Welcome back. All right, so after doing what seemed like a completely illegal thing and treating that du dx as an actual fraction, let's see if we can justify why we could treat it as a fraction and get the right answer. So the question is, why does U substitution work? So suppose we're trying to find something that looks like it came from the chain rule. The antiderivative of something that looks like it came from the chain rule. So we've got f of g of x and then times g prime of x. So the fact that we have g as an inside function and then times g prime makes us think chain rule, right? So, and suppose that we know an antiderivative of little f called big F. So we know big F prime is little f. So this thing, which I'm calling number 1, this is the same as writing what? Little f is the same as big F prime. So I can write that as big F prime of g of x times g prime of x dx. And now this should totally remind you of the chain rule, right? This is the chain rule applied to the function big F of g of x. So that's what this equals. Big F of g of x plus c. Okay, so let's keep that in mind. That was without doing any u's. Our goal here is to show why we can replace this, what I'm calling number 1, with this crazy looking thing over here, f of u du. On the other hand, if I call this intermediate middle function g of x, then how can I write this? I can rewrite this as, this is the same number 1 that we're trying to evaluate here. F of u. Now what is g prime of x in Leibniz notation? If u is g of x, then g prime is du dx. And then the dx just stays there. But what is this? This is the same as writing big F prime of u times the derivative of u dx. And this also we can see came from the chain rule, because I've got the derivative of a function with the inside kept the same, and then times the derivative of the inside. So this is big F of u plus c, or big F of g of x plus c. In particular, this is what we want to remember, I think, that this number 2. So we figured out that this number 1 was equal to this thing, which we're calling number 2 here. I didn't really need to write this last line here. But what do we also know? If somebody just gives you this simple-looking integral, and you know an antiderivative of little f is big F, this is just equal to big F of u plus c. So I'm going to call this 3. So what have we figured out? We have figured out that expression 1, what we're trying to find, is equal to expression 2. And we have figured out that the expression 3, f of u plus 3, is equal to expression 2. So since 1 equals 2 and 3, or 2 equals 3, then by this fancy thing called the transitive property of equality, if 1 is the same as 2 and 2 is the same as 3, then what must be true? Then 1 must be the same as 3. That is, what was 1? 1 was this thing, what we're trying to compute, f of g of x times g prime of x dx is the same as, in other words, equals f of u du. It just looks like we are canceling these dx's here. I mean, that's why we are allowed to cancel the dx's mechanically when we're doing this substitution. But you notice that here we never did any illegal canceling. We never treated du over dx as a fraction anywhere on this chalkboard here. What we did is we said that this thing here is equal to big F of u plus c. But this thing here was also equal to big F of u plus c. So therefore, this thing must be the same as this thing. And therefore, you can pretend like you're canceling these dx's and see that that's, and not cause any harm. Since we know that this expression is the same as this expression, if we pretend that we cancel those dx's, well, they're still the same because they were the same in the first place. That's my way of explaining why this U substitution works. I've tried a variety of ways over the years. One time after I gave a long explanation, sort of like this, somebody raised his hand and said, but why does U substitution really work? So I hope that this gives you some idea about why it works, why we're not really canceling not really treating this as a fraction and canceling the dx's. It just looks like we are. And mechanically, it's the part of the beauty of the Leibniz notation that it's not really a fraction, but we can pretend like it's a fraction and get all the right answers legally. And this is the legal explanation for why that works. And if you're not interested in all this legal explanation, that's fine. Anytime you do a U substitution problem, you can always check at the end, take the derivative. Did you get what you started with? And if you did, then your U substitution was correct. So in our next segment, we'll practice doing some U substitutions.